So a factor is a special type of vector which is used to represent categorical data. So, and there's two types of factors. There's unordered or ordered. So you can think of this as being storing data that have labels that are categorical but have no ordering. So, for example, male and female. Or you can have ordered factors which might represent things that are ranked. So they have an order, but they're not numerical. For example, in many universities you'll have assistant professors, associate professors, and full professors. Those are categorical, but they're ordered. You can think of a factor as an integer vector where each integer has a label. So, for example, you can think of it as a vector as 1, 2, 3, where 1 represents high, and for example, a high value, and 2 represents a medium value, and 3 represents a low value. So you might have a variable that's called high, medium, and low, and underlying in R is represented by the numbers 1, 2, and 3. So factors are important because they're treated specially by modeling functions like LM and GLM, which we'll talk about later, but these are functions for fitting linear models. And factors with labels, generally speaking, are better than using simple integer vectors because the factors are what are called self-describing. So having a variable that has values male and female is more descriptive than having a variable that just has 1s and 2s. So, for example, in many data sets, you'll find that there'll be a variable that's coded as 1 and 2, and it's not easy to know whether that variable is really a numeric variable that only takes values 1 and 2, or whether that variable is really, for example, representing gender, and the 1s are males and the 2s are females. But the problem is that's not something that's coded in the data set, so it's hard to tell. If you use a factor variable, then the coding for the labels is kind of built into the variable, and it's much easier to understand. So factors can be created with the factor function, and the input into the factor function is a character vector. So here I'm just creating a simple factor which has 2 levels, and the levels are yes and no. And so x is a factor, and you can see it prints out a little bit differently from a character vector in the sense that it prints out the values yes, yes, no, and then it has a separate attribute which is called the levels. And so the levels of this factor are no and yes. Okay, so there's only 2 levels. I can call table on this factor, and it'll give me a frequency count of how many of each level there are. So, for example, it'll tell me that there are 2 no's and there's 3 yeses. Now, the unclass function strips out the class for a vector. So, for example, if I call unclass on x, it'll kind of bring it down to an integer vector, and you can see that underlying the factor is represented as 2, 2, 1, 2, 1. So yes is coded as 2, and no is coded as 1. Now, it's not really essential for you to know this because you can just treat the factor as being a vector of yeses and nos, but sometimes it's useful just to know underneath kind of how factors are represented by R. And so you can see it's really an integer vector with the levels attribute of no and yes. The order of the levels in the factor can be set using the levels argument to factor. And sometimes this is important because in modeling functions, when you include a factor variable, sometimes it's important to know what the baseline level is. And so the baseline level is just the first level in the factor. And the way this is determined in R is critical. It's determined using alphabetical order. So, for example, if I create a factor variable with the elements yes and no, then the baseline level will be the first level that's encountered. And because no comes before yes in the alphabet, then no will be the baseline level and yes will be the second level. Now, this may not be something that you want. You might want, for example, yes to be the baseline level and no to be the second level. And then in that case, you have to explicitly tell R that yes is going to be the first level. And you can use that using the levels argument to the factor function. So now when I print out the x object, you see that the elements are still the same. It's still yes, yes, no, but the levels attribute is reversed because yes is the first level and no is the second level. So there's a special type of object that we haven't talked too much about yet, and these are missing values. Missing values in R are denoted by either NA or NaN, which we talked about before. NaN is used for undefined mathematical operations, and NA is pretty much used for everything else. And so there's a function in R called is.na, which is used to test objects to see if they are NA, to see if there are missing values in that object. There's another function called is.nan, which is used to test for NANs. So NA values can have a class too. So you can have missing integer values, or you can have missing character values, or missing numeric values, etc. And so even though it looks like it's all NAs, the NAs can have different classes potentially. And then an NAN value is considered to be also NA. So for example, an NAN value, a NAN value is missing, is considered to be missing. So, but the reverse is not true. So an NA value is not necessarily a NAN value. I've got a few different types of missing values listed here. So here I created a vector x, which is 1, 2, NA, 10, and 3. So now this is a numeric vector, and the NA value in here is going to be a numeric missing value. So when I call is.na on x, what it returns is a logical vector. And the logical vector indicates whether each element of the vector x is missing or not. And so there's only one missing element in this vector, and so that's the third element. So you can see that the logical vector that's returned, the first two are false, the third is true, and the fourth and the fifth are false. So the element that's true indicates where the missing value is. If I call is.nan on this vector, you'll see that the vector that's returned is all false, because there aren't any NAN values, there aren't any NAN values in this vector, so everything's false. Of course, if I create a vector that has a NAN value in it and an NA value in it, you'll see that is.na returns true for both of them, but is.nan only returns true for the value that's actually NAN. The last data type I'm going to talk about here is the data frame. The data frame is a key data type used in R, and it's used to store tabular data. So of course, tabular data make up a lot of what we use in statistics. Of course, not all types of data are tabular, but because so much data becomes a tabular form, data frames are very important in R. So data frames are basically represented as a special type of list, where every element of that list has the same length, right? So you can think of each column of the data frame as an element of the list, and of course, in order to be a table, every column has to have the same length. However, each column doesn't have to be the same type. So the first column could be numbers, the second column could be a factor, the third column could be integers, the fourth column could be logicals. It doesn't matter what the different types are. So unlike matrices, which have to store the same type of object in every single element of the matrix, data frames can store objects of different classes. And so data frames also have some special attributes. The first special attribute is called a row name. So every row of a data frame has a name. And this can be useful for kind of annotating the data. So for example, each row might represent a subject enrolled in a study, and then the row names would be the subject ID, for example. However, sometimes the row names are not interesting, and often you'll just use row names of 1, 2, 3, etc. Data frames can be created by most often calling the read.table or the read.csv function, and we'll get into that a little bit when I talk about reading data into R. And you can also create a matrix from a data frame by calling the data.matrix function. Now you can't, if you have a data frame that has many different types of objects, and then if you coerce that into a matrix, it's going to force each object to be coerced so that they're all the same. So you may get something that's not exactly expected. So data frames can be created, besides using read.table or read.csv, you can use the data.frame function. And here I've created a very simple data frame where the first column is the foo variable, and the second column is the bar variable. The foo variable is an integer sequence from 1 to 4, and the bar variable is a logical vector with 2 trues and 2 falses. So when I auto print the data frame out, you'll see it prints out the 2 columns, and here the row names, since I didn't specify any special row names, it just defaults to 1, 2, 3, 4 because there's 4 rows. And then when I call the nRow function on X, I see that there's 4 rows, and the nCall function shows me that there's 2 rows. R objects can also have names. So this is not true for just data frames, it's true for all R objects. And this can be very useful for writing readable code and self-describing objects. So for example, I'm creating a vector that's an integer sequence 1 to 3, and by default there's no name. So when I call the names function on X, it gives me a null value. However, I can give a name to each element of the vector X. So for example, if I can say the first element is called foo, the second element is called bar, and the third element is called north. So now when I print out my x vector, I get a vector 1, 2, 3, but then each one has a name over it, which is the name I just specified. And so when I call the names function, I get the names that are associated with each element of the vector, foo, var, and north. Lists can also have names. And so, for example, here I'm creating a list with the list function, where the first element is called A, the second element is called B, and the third element is called C. And so when I print out the list, it prints out the names of each element and the values associated with those names. Finally, matrices can have names. These are called dim names. So here I've created a matrix from the sequence 1 to 4. It's a 2 by 2 matrix. And so when I use the dim names function, I pass it a list. I assign it a list where the first element of the list is the vector of row names, and the second element of the list is a vector of column names. So here I want to name the rows A and B, and I want to name the columns C and D. So that's what I pass to the dim names function. And now when I print out my matrix, I can see that the row names and the column names are labeled as I wanted. So that's kind of the whirlwind tour of the different basic data types in R. So far we've talked about the atomic classes, so numeric, logical, character, integer, and complex vectors. We talked about how vectors can only have elements of the same class, and the main exception to that is lists, which can have elements of different classes. There are factors, which are used for coding categorical data, both ordered and unordered data. There are missing values that are represented by NAs and NaNs. Data frames are used to store tabular data, where each column can be of a different class. And finally, all R objects can have names, which can be useful for creating self-describing data.